I'm very excited to present our robotics seminar speaker, Professor Zeynep Temel. Professor Temel is an assistant professor with the Robotics Institute at Carnegie Mellon University. Her research focuses on developing robots that can mechanically conform to the environment or objects that they interact with. Prior to joining the Robotics Institute, she was a postdoctoral fellow at the Microrobotics Lab at Harvard, and she has received her PhD from Sabancı Sabancı University in Turkey. In 2020, she was selected as one of 25 members of the Young Scientist Community of World Economics Forum. We have met a few years ago, and I still say the story. I remember the first time I saw the work, Professor Temel's work. She presented this incredible robot. I don't know if you remember that or not, but it was this incredible robot inspired by trapjaw ants, and the robot was, smaller than your pinky nail, and it could jump 40, 50 times its body length. It was the most impressive robotics demo that I have seen ever, and it's still one of my top favorites. So, anyways. Huh?
It's still not published.
Well, I am waiting. I am waiting for it. It's an incredible robot. I can, anyways, it was my favorite. So, welcome to Princeton.
Thank you so much. Can I not use this now? I don't know.
I think you have to maybe speak in the
Okay, so I will just turn this off and then keep talking like this. I hope it's okay. So in that presentation, since I don't know of meeting, since I know that Amy would be there, I actually start my talk with Click Beetle videos to get her attention. And I didn't know that she was already interested in what I do, so I was like, yeah, I just put Click Beetle there because I'm a fan of your work. That work is still not published, and I'm not talking about that. And thanks for the motivation. I guess I will go to lab and work on it, and then finish the paper after my trip here. Anyways, today I want to talk about adaptable robotic systems using embodied intelligence. You probably are seeing this combination of these words one way or another around nowadays, right? I assume. And if you are working in robotics, probably you can give a similar talk, like a talk basically under this title. I'm very I'm 95% sure that I can find a relevance of your work in this domain. But how I approach to this is what I want to share with you today. So when this robotics all started, this was our, domain or problem, right? Agreed? Okay. We were all interested in automating the dirty, dull, dangerous, correct? Right? Okay. Is it still the case? Yes? Yes? No? Yes and no? Every answer is good answer here. I will say yes. We still have a lot of problems in the industry that we are not able to, or we couldn't figure out how to solve in a robotics domain, in an automation domain. But at the same time, we have a very good understanding of this space, which is a very structured environment. We can basically design our space to solve the problem. Sometimes we can even change the problem definition, right? And then design everything to the need. I would say nowadays, though, we are more interested in this kind of environments and developing robots for these kind of tasks. Still dirty, dull, and maybe sometimes dangerous. Depends. But we are more interested in compact solutions that can work in many different environments that might be structured or unstructured, depending on how tidy you keep your room. So what are we going to do? How can we actually solve this problem? Or is this problem solved? Because you see that there's a robot vacuum there. Is this problem solved? No, why not? Because I was looking to Amazon, and then I saw that you can basically buy a robot, and this is the advanced version, the pro version, for $4,000. It will be delivered into your doorstep, and then put some algorithms on it, and it can do whatever you want. So we are done. End of the presentation. Especially now, there are so many good learning algorithms that we can actually, put on that robot, and then they can probably learn doing very complicated tasks. So is this still not solved? So can I, if I buy this robot for $4,000, plus probably tax, can I actually use this robot in these kind of environments? Or what would it take? So I basically picked these environments because I am interested in them. I don't want a cooking robot, but I want a helper robot in the kitchen, or maybe cleaning robot after I cook, because I'm a messy cook. But search and rescue, we have been talking about it since the start of the robotics probably, and still we don't have robots in the search and rescue fields working, doing what the first responders are doing. Agriculture, under the sun, really very delicate work sometimes. Can we actually automate it? It will be very efficient if we can automate that work. And the environment can be muddy, dry, very different kinds of environment. And the healthcare. So in a recent actually study that my colleague did with nurses and patients, they figured out that the patients need more time with people. They want to interact with nurses. But since nurses are too busy, they have to take care of many, many patients. They just come and do the task and then go. So if we can make a helping robot, not replacing the nurse, but to help the nurse, then the robot can prepare whatever the nurse needs, and the nurse can actually interact with the patient, which would actually help with their mental health as well. So can we, again, let's go back, get this robot, and then do all of these tasks? I say no, and then I see a lot of people agree with me in this room. And I want to focus on the tidiest environment here in the kitchen. Let's see what we can do. So I told you that I don't want a robot cook for me because I like cooking, but I want to tell the robot that, hey, open that pantry cabinet and then take that jar and open the jar for me, whatever jar I'm interested in. So how can I make a robot open that jar? So when I first thought about that problem, it was very easy. I was like, why can't a robot open a jar? Excuse me, didn't we figure this out? My colleague and friend, Oliver Cromer, was like, oh my God, I need to educate you in manipulations. It was a journey. At the same time, so with all the robots that we have around, I say this is still a challenging task. You will love this slide, the next one. If I actually put an octopus in a jar and then close the lid, it can figure out how to turn the lid and open the jar and set itself free. None of those limbs are designed to do this task. They're not rigid, fully rigid, right? They are basically not made for this task, but they can figure out within minutes. So what is the secret here? We have great robots and they cannot, but these kind of animals can, although they're not designed for it. So my take, and I'm happy to discuss, is that the robot hardware is what is actually keeping us back, or one of the major things that is keeping us back. So I think embodiment dictates the upper bound of adaptability of whatever algorithm you have. So then, if we want to make robots more adaptable, how can we make them? I approach this problem from two different perspectives, from manipulation and locomotion, which are the main features of robots that we have around, right? So I will show you a couple of examples from my lab today. This is all the people that are working on these projects. I'm not taking credit. I'm just seeing them once or twice a week, and then we talk, and then I'm like, oh, wow, it's amazing. Keep going, and maybe look at this idea, and and they are doing the fun work in the lab, so I'm proud of them, and then I'll share their work. And we are a very friendly lab. If you are curious about any projects, please do not hesitate to reach out to these students, and they are more than happy to talk to you anytime. Okay, let's start with the manipulation. For me, manipulation all started with the Delta robots. If you don't know what Delta robots are, they're basically they have 3 degrees of freedom. They're manipulators. They're very fast. The 3 degrees of freedom are in the translational domain, so X, Y, and Z. And all the mass, all the motors are at the base, at the top. That's why the linkages are very lightweight, so they can be very fast, precise, and accurate. We really like them for pick and place motions, especially when we don't want people to touch what is being pick and placed, like food or medicine, that kind of stuff. So when I started at Professor Wood's microrobotics laboratory, I was looking for a fun project to learn the fabrication tools that they have, which was the laminate fabrication, like everything at small scale. You cannot use screws, nuts, bolts. So I was like, oh, maybe I can work on making a Delta robot at very small scale with sheet materials. So this was my first project at Harvard. So we built this super fast Delta robot. You can see all these triangle pieces there are piezoelectric actuators. They can work very fast. Like each actuator has 75 to 100 hertz or 100 plus hertz frequency. Although the workspace is very little, we have very accurate and precise motion. And what we actually realized is since this is very compact, we can use it for handheld surgical tools to stabilize the hand tremors that the surgeons have. So I have the Delta here, and you can look at it. There is no hair inside, so it looks like a hair at the table, so please do not try to take care of it. I know, I'm sorry. I was just giving the Delta robot to the audience. So if you are trying to take the hair inside, it's not the hair, it's the cable, so please not try that. So anyways. Okay, so, and then after this work, I was presenting it at Carnegie Mellon, where I now work, and Professor Cromer, Oliver here, was like, oh, your Delta robot is amazing. Let's make a hand with all these Delta robots. They can be great fingers. And I was like, this was 2018. It was my interview. And I'm like, I don't know about manipulation, but I think there are a lot of hands in literature. So I was actually right. These are all the hands since the start of the hands in robotics to 2018. And I was like, why do we make a hand? Like, there are already so many people working on making hands. Does it actually make sense? And since then, 2018, there are actually more hands you can see in all sorts of, like, with all sorts of materials, manufacturing techniques, scales, and everything. So honestly, making a Delta hand seemed very ridiculous to me. So I was like, I'm really not sure about this idea. So we should really talk to some other people to see if it's actually, viable or meaningful or not. So Oliver said that, okay, I know two people, Professor Edmoni and Mason, Henny and Matt. If you don't know Matt Mason, he is one of the founders of robotic manipulation. And we presented them this idea that we can actually, work on building some manipulators, some grippers or hands that have fingers with multiple degrees of freedom that can perform dexterous manipulation tasks that might be useful to open a pill bottle and then take a pill and then feed to humans, patients. Good idea, but then these manipulators should be soft if they're interacting with, or safe if they're interacting with people, and they need to be strong enough if they're opening a pill bottle. Like, you apply quite a bit of force when you try to open a pill bottle. So safety for human, and we want it to be accessible, so it needs to be cheap because we want it to be available for everyone. And then we want many of them because we need these dexterous motions. So we thought that living hinges, if you know living hinges, they are basically embedded joints in the structures, are probably best way to go if we are thinking about the cheapest manufacturing technique and easiest manufacturing technique, which is 3D printing. This is where we started. We first characterized the parallelograms, which are the key features of the Delta robots, Delta mechanisms, and we immediately noticed a problem. I don't know if you can detect it. So I told you that Delta manipulators have X, Y, and Z motion, right? So they don't have any kind of rotation at the end effector. But you can definitely see the rotating end effector there. So there are advantages and disadvantages to this. So first of all, if that rotation is happening, then I want to be able to control it, or I want to be able to know when it is happening at the very least, so I can actually learn the behavior of my manipulator. And then second of all, I actually don't want it all the time, because that 3 degrees of freedom is very helpful for me to do some certain tasks. So we studied different materials, different dimensions, and we figured out that, there's a good solution. We can do that actually if we keep, materials and dimensions, characterize them properly. And if we go out of a certain space, a certain workspace, then the end effector will start rotating. So we can actually use that too to our advantage. So to demonstrate this, and this is the capabilities of delta fingers, we put 2 of them together and then made a gripper. There's a difference between the previous slide and this one. If you can see here, now I have the linear actuators instead of rotary actuators. That is because I want to make everything compact, and from now on I will show you mostly the linear actuated deltas. So even though they are 3D printed soft end effectors, you can see that, this is the obligatory robot hitting video that we needed to record. They are pretty robust into different forces. And we actually show that if we add some different fingertips, we can do different kind of dexterous manipulation tasks. I didn't know that these tasks were the tasks that most manipulation people were interested in. But here we are picking a card from, a single card from the deck. This task was very difficult because apparently we need to apply quite a bit of force to get the grape out of the stem. But we were able to do that. And in the last example, you will see that, let's get the grape first. Yes, grape, amazing. And we are not squishing the grape, if you notice. And we can do the dough manipulation. So this was actually very interesting for us because soft robot, soft body interaction was really interesting to look at, both from robotics perspective and also the dynamics perspective. So it was a little bit challenging, and they're all teleoperated, you can see here. But eventually we showed that, oh, okay, we can do that. So once we had 2 fingers, the next natural step for us was building a hand. And this is basically what we did. So here the graduate student Zeynep is putting everything together. You can see all the materials here. If they're not 3D printed, then they are both, they're like screws and nuts, it's fine. And then the plates are laser cut. So very cheap, very fast. You can manufacture it within minutes, maybe a couple of hours. Again, we wanted to test it with, if it is to see if it's strong or not. And then we studied different synergies. So I told you that delta robots have 3 degrees of freedoms, which means that they have 3 actuators, right? But if I put them in this kind of a configuration, then I can actually study coupling of the actuators if I want to. So I can couple some of the actuators together, some of the links together, and then I have 9 actuators. I have here a 5 actuator one. I'll just pass this again. Since they were traveling with me to a lot of places, they are actually a little bit, what's it called? Not super robust, because I think they're broken in my luggage and, and backpack, but still you can get the idea. So we studied the synergies between the actuators and linkages. So if we have 5 actuators, 9 actuators, 12 actuators, what kind of tasks we can do. And you can see here that there are a lot of different tasks that we were able to manage. And Zeynep is using the leap camera and then teleoperating with the finger motions. And then we thought that the easiest mapping is between 2 fingers of your both hands to the 2 fingers. And you can see we also did a lot of dexterous manipulation tasks. Yes, you can hit it. Again, they were in my backpack with a lot of things on top. It's totally fine. So there were a couple of problems, though. Still, we didn't. We wanted to see more, definition in the motion. So instead of printing them from a single material, we switched from this to the multi-material 3D printing to make the links a little bit stronger. And then the next thing is that the control of this hand was not the easiest thing with the camera there, as you can see, because like if you are moving your hand, you're not like always at the same altitude, and it was affecting the control. So that's why, and also it was affecting the teach robot how to do the tasks. So what we did is that you can see the difference now in the color. This is a multi-material 3D delta. We also built a twin of the delta. We call it a mechanical twin or kinematic twin. You can see the sliding actuators there, and then we call it the delta hand. And we took the data that is coming from the camera in the palm, in the middle of all the deltas, and then we took the joint states, and we did some magical learning stuff there that is totally out of my domain, so I'm not talking about them as a mechanical engineer. And we performed some training for the Delta robot with this teleoperation system. And the Delta hand was actually able to learn a lot of these tasks from like a few training data. Like, we performed 20, 40, 60, 100, and then the success rate was really good. And we also generalized it from within different kind of tasks, from like rolling a ball in the hand. Syringe was really difficult, so we actually did a syringe push. Shape insert is a very also like classic task that we did. But we basically performed a bunch of dexterous manipulation tasks very successfully. So then things took some turn because we were like, oh, okay, this is what we think. Like, I like the kinematic twin better. It makes sense because I like, hands-on things. But would people actually like that too? Like, what is the best method to teach people how to train the robots? What would be the preferable way? So we did some user studies. So we asked people to control the robot either through a kinematic twin or a visual tracking system, and then collected a lot of data. Oh, thank you. You can keep them. Not until the end of the Okay, and then we ask people to perform these 3 tasks. Basically, it is a block sliding task, but it gets difficult and difficult, more and more difficult, because we are changing the angle about how you slide the block. And the results were actually very interesting to me. So I prefer, again, the kinematic twin, because to me it was more like, oh, I can map in my mind what is happening. But apparently most people actually thought that, because task completion times were shorter with the kinematic twin. The success rates are comparable, but within the trials, the learning rate of people really got significantly lower. Like, they really quickly grasp the concept if you have a kinematic twin of the teleoperation system. So it is, I'm not a human-robot interaction person, but Henny is helping me understand this data even more. So I'm very excited about where we are going with, next with this one. Okay, so one finger we had. You have a question? Yes.
I saw the video of it opening the little
Jar.
That was really cool. And when I was playing with the robot finger, it was really compliant.
Mm-hmm.
So what are the mechanisms by which you do that is like locally stiffening so you're able to apply force to open the door? Or is that something, like how you're applying force but at the same time it's really compliant? So
Yeah. Yeah, so we really wanted it to actually how can I say, buckle after some forces if you are especially designing this to interact with people, right? So I don't want the robot to be able to apply a lot of forces. So we did a lot of studies about where should the actuator be located to apply enough force for these kind of tasks. So it was modeling and experimental studies about what is the design of this robot so that I can get enough force to do these things, but also buckle when I need to. Yeah. Okay, so we have one finger. Cool. We put 4 of them together, made a hand. Great. What's the next step? What? Yeah, maybe. It's actually a good idea. We studied the 3rd finger thing, the thumb thing. It's not published yet, but we are working on it. But we wanted to go crazier. And to some people, the next thing is the craziest setup at Carnegie Mellon Robotics. Why not we make like 64 of them? I see some faces and I'm like, why? Come on, we want to have fun. Look at this, isn't it cool? So you can see a lot of these kind of examples actually in literature. Most of them are doing like 1 degree of freedom motion, right? This all array of robots doing 1 degree of freedom motion. Here we can do like 3 degrees of freedom. So we can actually study a lot of different tasks. We can divide the robots into groups. They can do like different tasks at the same time. They can deal with multiple materials at the same time. They can create structures like walls to basically help them, like, you know, and this is a great problem, a great control problem. How will we control these robots? They're all compliant, soft. These are not multi-material. These are all TPU. So how will I actually control 192 actuators, if I did the math correctly, you know, in a meaningful way in the space? And why did I do that? Because again, I want a robot to help me to cook. So I want to turn this robot upside down, like in this, you know, photo. And I wanted to open a dough for me so that I can make pizzas or whatever I want to, right? So in order to do that, so you can see that this has nothing on top, this setup. But in the next one, we added some fingertips. You can see, so that we can actually interact with objects easier. And those fingertips are inspired by our own fingertips, have a rigid core and a compliant shell, so that we can actually capture the materials better. I'll only show one video, and I'll tell you what the problems are we are facing. So this is the first time we were actually able to take a block and lift a block on air using a couple of them. Because first of all, again, kinematics are not very well known. We have a camera, you see here under the setup, but most of the time, if you are looking for it with the camera, the block is blocking some of the robots, and sometimes the robots are blocking some of the robots, so it is not the best way to control. And there are 64 of them. So it is kind of a multi-agent control problem. How are we actually, and multi-agent learning problem, how are we going to find the right way to control? So we are now working on this. I'm very excited. I know saw the faces. It's a crazy setup, but I think it is a great setup to learn about all these like different kind of control and learning problems. Okay, one last thing about this. What we also did is we basically turned this into the Delta robots, I mean, a very affordable learning tool for robotics. So this is Delta Z. You can see all the parts here. They're all online in GitHub. You can find how to design, how to make, where to buy the components. You can also design and build your own end effectors and then like put them together. We also put together a user interface for you to play and learn. And then we made a curriculum around this robot. So this robot is around $50, so not really very expensive. And you can actually teach everything about robotics. This is what my claim. You can teach everything about robotics using this, from design, manufacturing, because you can also use different manufacturing techniques, right? From actuators, how to control them, what kind of sensors you want to use to control them. If you want to actually apply some learning algorithms on it, if you want to do computer vision for it. And also, this is what my summer school students did. They said that, oh, we want to make a walking robot, like a moving robot. And I'm like, this is a manipulator. Why do you want to make a walking robot? But they added some wheels, as you can see on the videos, and then it turned into a walking robot. So you can even teach manipulation or locomotion using this robot. Again, this is all open source. You can find it online. I'm organizing another summer camp using this robot this year. I'm very excited about it because it's just fun to see how students are also bring their own ideas. Okay, maybe this is a good time to switch topics from manipulation to locomotion. So I will talk a little bit of collaborative robots to show you how I can make the locomotion more adaptable to different scenarios. So for me, this all started with this video where army ants are coming together to build a bridge. The smart or the interesting thing or amazing thing about army ants is that they can actually build this bridge and then change the shape or structure of the bridge with the changing conditions. So they are adapting to dynamic environments. The other thing is that they are so very smart, although they are super tiny. So for example here, they are not going all the way up and coming down, or they are not creating the bridge here. So why do they pick this, like, you know, how do they optimize their path there and then make the, you know, bridge there? How do they know how many robots they need to, how many ants they need to bridge, to make the bridge? Like, how do they know how much load they need to carry? Like, they are all very interesting questions. So we thought that if we can figure this out, then we can basically make robots to work in, you know, disaster zones. Okay, so what do I want? I want to make reconfigurable collaborative robots. I want them to work individually, like ants, but I also want them to come together to overcome obstacles. And many different kinds of obstacles. They can be like negative gaps, or they can be positive gaps. They can be just step downs, right? Different things. I want them to be energy efficient, because this is one of the problems in those kind of fields. And I want them to be strong enough to perform the tasks that I want them to perform. These are the puzzle bots, the first versions of that. You can see they are like nothing like ants, or they look nothing like ants. But at the end, that's not the purpose. The purpose is to study their behavior and see if we can do the same things with robots. Here is the first video that my graduated student, Yisha, recorded, which I really like. So they form a bridge and then cross the gap. And not only they can form a line, but they can also form a mesh structure to, you know, cross bigger gaps, because now they are stronger. But they suck at something, which is the uneven terrain. Because at that time, their connection was rigid together, like, you know, and then they connect through knobs and holes, and that rigidity really didn't help them to cover those kind of terrains. The other thing is this. They fail terribly if they are trying to take a step down. So the solution to this is we needed a flexible attachment between the robots. And again, I am very frugal with respect to like adding actuators or sensors to robots. So I was like, I don't want it to be active, I want it to be passive. So Yisha designed an anchor mechanism that is easy to connect and difficult to disconnect. And we did some experiments with those robots. So I have a couple of them here. I'll pass them around. One of them is not very well assembled, so you can actually see what's inside. I like this. Yeah, I wish I could carry the 64 error. Anyway, okay, so this is how they attach and detach. You need a little bit of a wiggle between robots to detach. It's very easy. Now, because they have the flexible structure, they can actually take turns, which is really helpful for us to clear these kind of environments. Now they are successfully actually going across these kind of terrains. Do you have a question? Okay, sure? Okay. And the other thing that we can do is they can now take a step down, I think. Yeah, come on, you can do it. Yes, come on, yes. Yes, they can do it. And then I was fortunate enough to work with James as one of the summer undergraduates in my lab a couple of years ago. He is now a graduate student at Santa Barbara, UC Santa Barbara. He said, hey, I really want to add another actuator because not only stepping down, I want them to climb. And I said, okay, fine, I'm caving, add another actuator. So this is what he did. And this arm is helping not only to step up, but also to step down larger distances. And also, with the other actuator, we can now push the robots to the surfaces that we cannot reach, so they can keep exploring. I think one of my favorite things about this video, if you will look closely, I don't know if you can see there, there is an ant like walking there in the robot. It's so funny. Okay, so what I learned from this project is that not all the robots should be the same if I want to perform bigger tasks than the robot, right? I really value the heterogeneity here. So how can I make it even more heterogeneous? Because I think those robots, although capable, and I can keep working on them to make them more and more capable, would not be super useful to clear this area. Because still, those robots have small batteries, as you can see, and then we keep adding more stuff on them to make them more and more capable, right? So that means that I am increasing my energy consumption. So if I want to get into these kind of environments, even like, after a few meters, my robot will be dead. So what can I do? So I was brainstorming with my colleague, Professor Mel Martinez, and my colleague from Purdue, Laura Blumenschein. And then we said that if we had a bigger robot to carry our small robots to the field, we could probably figure this in a better way. But I was like, I don't want any big robots like the robot dog because they're loud and they're really not squeezable. And I think the sound is my biggest thing because in this kind of environments, you really want a quiet operation to hear possible survivors, So we came up with this idea. Laura is working on growing soft wine robots. Have you heard about wine robots? If you haven't, they're basically like a plastic bag, and they're growing from inside to outside, and then they can go to meters long distances, and they're very quiet. And since they are soft, they can actually squeeze themselves into very small areas. And we have the small robots, so if this wine robot can carry the small robots to the location, then my robot doesn't have to spend all the energy to go to the region of interest, but just do the job there. And then my small robots can help the wine robot to take serious turns or change the diameter to actually reach to even further distances. So can we make that happen? So you can see a wine robot there, and this is what we designed. We call them rescue roller. Again, a very simple design. These are our first experiments. So we are loading one of the rescue rollers inside to the wine robot. And then, yeah, you can see the rescue roller is moving inside, and then you can see here how rescue roller is pulling the wine robot to change its direction. So this is one of our first demos, the same experiment from two different views. The rescue roller, we now have different versions of this, but this is one of the, again, I'm only allowed to take, these kind of demo pieces. So you saw that the rescue roller came out and then pulling the wine robot to change its direction significantly so that it can actually grow towards this hill or incline. Let's wait a little. And you can see the other rescue roller coming as the wine robot growing. And once it's there, it can deploy another rescue roller, and then it can work on that environment as well. So this is the concept, but the study in real world is a little bit challenging. So we put together a simulation environment where we basically introduced different environmental features like gaps or hills, and also some points of interest like temperature, high temperature, or humidity. And we did a couple of experiments. I think you can see here if wine robot and the rescue rollers work together, we have a higher coverage of the environment. And actually, this is a better view of that. So on the top left, you can see wine robot with rescue rollers, and rescue rollers are deployed in every minute. And here it is wine robots only, and that is rescue rollers only. And here there is no intelligence in the robots. So they're just doing random motions. So even with the random motions, first of all, we get a big difference from like only wine robot. So you can see that coverage is 50% there if you are using only rescue rollers, which is not bad. But coverage reaches to 63% if you use both of the robots together. So this is actually quite high. And again, there is no intelligence in these robots. So if we are adding the intelligence, which we are now working on, then we can actually make it even better. Okay, it's 11:46. I also have a couple other projects to show. Like, these are not the only robots. We have a bunch of other robots that we are working on. Like, turn the delta hand upside down and then make a walker, like the hand. This is one of the fun projects that we have. A collaboration with Professor Ryan St. Pierre in the University of Buffalo about a really centimeter scale, 1 centimeter scale multimodal robot, and that is untethered, that can jump and also crawl. And then there's a shape-changing swimmer, again, multimodal locomotion robot that can swim undersea, sail on the surface of the sea, and then walk on land. So I want to stop here, and I hope I convinced you a little bit of how I'm trying to make the manipulation and locomotion in robots adaptable with these robots. Oops. Where are my robots? My robots are not coming. With these robots, yes. Yeah, and thank you for joining me today, and I'm happy to take any questions. I told you I speak fast.
All right, we have time for some questions. All right.
With the puzzle robots, how you said you wanted them to it to be easy to snap them together, but then hard for them to come apart. Were you able to detach like as the robot, and if so, how hard of a maneuver was that for the robots to purposefully detach, if they could?
It was not difficult, but it was very, so these versions are, again, demo versions. If you played with them, it is actually easier. So we figured out a good design that gives us my requirements, basically. So it is easy to push in, but harder to push out. So it is almost, I think it is in paper. If you like have a robot and a soft anchor attached, and then have like 10 robot chain here, it can still hold. So it will not get detached. So you have to have this like wiggle motion to detach. And it's not difficult for those robots to make. This is the question, or did I understand correctly? Yeah, okay. I think I saw a hand over there. We have more microphones.
Thank you for the inspirational talk. I have a question about the scaling. So when you the first prototype you showed the Delta robot, I saw it's a millimeter scale, and then when you make it a hand, I think the robot is like more like a centimeter scale. Mm-hmm. So how would you select this centimeter scale instead of millimeter scale? Mm-hmm. Or in other words, would be advantage when we do a hand with millimeter scale?
So okay, did I understand correctly? Why don't we make a hand in millimeter scale?
I think why you make the centimeter scale?
Oh, okay. Because of the task domain. Like if I want to open a pill bottle, this millimeter scale Delta robots that I showed, they won't be able to apply enough force because of the actuators that they have, right?
Yes.
They're more fragile, and the structures, they're more fragile. So those tools are mostly for like very delicate, more delicate tasks at smaller scale.
Right.
So I actually, maybe we can try to do like microorganism manipulation or that kind of things. But if you want to, I don't know, I don't have anything here. I'm not breaking your mics, I promise. But if you want to do this, this is hard with that millimeter scale hand. You cannot even like get around this. So most of the time, it is basically depending on your task and what you want to achieve. This might be not big enough for some other tasks. Right?
That makes sense. Also, just a curiosity, in terms of the puzzle robot, you designed it, the goal is to, for example, in a scenario that disaster rescue, what would you think would be the optimal shape or size of the robot for this type of task?
Yeah, I don't know. So from what we heard from the rescuers, like the first responders that we interviewed with, they really want, they said 5 centimeter, 5 centimeter, but 5 by 5 by 5 centimeter cube basically is the, the robot that can, that is able to do a lot in that kind of environment. So there were different kind of collapsure or collapsing. So some buildings just go sideways and then collapse and then like do a, a parallelogram kind of structure. Most of them apparently just collapse on itself and then become a pancake. And then sometimes they also have like the garages, the parking spots underneath, so they actually like go inside of the park. So there are different types of collapses. So I don't know if these robots are able to do all, are able to do work in all different kinds of environments. But from what we get from the rescue, the first responders, they said 5 by 5 by 5 is what you want to have the most. So that's why that was one of our requirements to design these robots. And again, this is the first version, so we are working on the other versions.
Thank you very much.
Yeah, you're welcome.
Hello.
Hi.
For the Delta robot, we saw that it's able to help stabilize like surgeons' hands.
Oh yeah.
Would it also be able, like with the telecommunication thing, to help those with like disabilities?
You are talking about the small one, or?
And then it like created the hand.
Yeah.
So would it be able to like attach to a chair to help?
Oh yeah, definitely. I don't know what the control mechanisms there are, but there are, like Henny is working on, my collaborator in this project is working on like watching the eye movements and then like controlling the manipulators and the end effectors. So we actually have different other end effectors doing that for people, like attached to the armchairs or the wheelchairs and like helping people with disabilities. Yeah, definitely.
Thank you.
While I'm walking the microphone, I have a question. It's very silly, but when you were showing the 8x8 Delta robot and it was moving the banana back, I don't know why I thought of crowd surfing in a concert.
Yes.
Yes, and I wonder now on the other side, as you scale things up for like to move very big things like human or more than that, what are some of the limitations for scaling them up, not in number, but in size? Are there any limitations that you can think of?
Yes. So, okay, so everything will scale up, right? Then your actuators will scale up, then the tasks will scale up, the weights will scale up, so you will need to actually like be able to carry whatever weight that you need to carry. So probably 3D printed Delta robots from like TPU wouldn't work in that scenario. The other thing is that I'm thinking about the design perspective. So I wanted to keep things like compact, so that I have, it won't cover the whole lab basically. But the thing is, if you are having big actuators and still like the size of the object, so it shouldn't fall between the robots basically, right? So what is the mechanism that you will have for this kind of like different conditions that like you shouldn't harm? At the same time, if you're thinking about like a warehouse, for example, big boxes of things that are manipulated, probably this is not the best way of doing that, because again, this is a very designed like structured environment, and you might not need the 3 degrees of freedom for that kind of thing. So it might be an overkill to do this kind of setup at larger scale. I actually didn't think about it also, like what we can do at larger scale if we have this system.
Like one of the things I was thinking about, and I want students to ask a question, but if you have, one of the, in hospital environments, it's really hard to move patients off beds and things like that. So, and I'm sure there are other mechanisms that you can use, but I can imagine a smart bed that can help transfer patients. And but anyways.
So everybody is actually seeing something different. Now that you say it, I remember, I think it was Chris Atkinson who told me to make a massage chair or a massage bed with these
I'll take that, yeah, okay.
And then Takio Kanade, I think, said that I want to do it like a vision table, like, using small deltas, like make a table that I can actually project on it, and then because of the texture is changing, like we can do it like a, vision thing. And then I think I'm forgetting who said it, but it might be Saad Bamla from Georgia Tech, said that, they actually look like if we can cover something, it can be like cilias, we can attach things, and it will be like, a million cilia. So there are so many possibilities if we scale up or down, I guess. Yeah, cool question. Thank you.
Hello, Professor. Thank you for your talk. It's very interesting. But I have a simple question. Could you please explain a little more about the kinematic twin? I'm still a little confused about how does it work.
Kinematic
twin. Yeah.
So it's basically the same Delta robot. Let me try to find the slide. It's the same Delta robot that we have. It just has here we go, right? So the same Delta robots that are kind of turned same direction. But they have some slider robots, so when we actually move, we can understand the position of the robots, the single Delta robots, and we can map it to the manipulator here doing the task itself. Is there a specific part that you're trying to understand, or like what?
Yeah. So does that mean that human has to interact with the machine by themselves, or in the left picture, the human has to teach the robot to act.
Mm-hmm.
Okay.
Yeah, it's teleoperation. So as I move the kinematic twin, like that telehand, then my robot moves. And then I'm trying, it is the imitation learning. I am basically teaching my robot how to act, or what kind of actions that it should do to put that shape into that, the pattern, right? There was another thing that I wanted to say, but I forgot. Also, one more thing. You said human interaction with robot. So keep in mind that there are no sensors at the moment on these robots. So we don't have the feeling, like this is not a haptic interface. So person, like the operator, doesn't have the feeling of what the robot feels. So this is another project that we are working on. What kind of sensors that we need for this, fingertips, so that we can actually understand what is happening there properly. Because it's not only the force, it's also sliding, right? They're twisting, like different kind of modalities there. So you won't be feeling like the forces that the robot's applying. So that is a little bit difficult. But still, people find it doable with the vision, or just looking at the robot itself.
Okay, thank you very much.
Yeah, you're welcome.
So thank you so much for the talk, and also thank you very much for bringing the hardware. It was really fun to look at them. Building on Amy's point about scaling up the Delta robots, I was wondering, coming from a swarm robotics background, if you've thought about each of the Delta robots as an agent in a swarm, and whether you can apply decentralized algorithms.
Mm-hmm. Can we talk later? Yes.
Yes,
You're working.
please.
Yeah, we are working on that, and I am new to the multi-agent domain with the puzzle bots, basically. And my collaborator at PuzzleBots, Katya Skara, says that first control one robot. If you can do it, control the two robots. If you can do it, control three robots, which is the most difficult part. And if you can do that, then you can do the rest. So I think now we can do the hand. I have hope for this setup, but still we are working, like it will be computationally so expensive too. So it is not only like, you know, I am working on resource constrained robots. So I don't want my robots to be inaccessible or expensive in any field, right, in any aspect. So how can I make it computationally also not expensive? So, but yeah, let's talk. Yeah.
Let's thank our speaker one more time.
Thank you so much.